Okay, everyone, welcome back. And in this lecture module, we're going to be discussing the concept and the way that nuclear magnetic resonance works. All right, it sounds complicated. It's not complicated. At least it's not meant to be complicated for you. And what you're seeing on the screen right now is a spectrum from an NMR readout. So, yeah, just like mass spectroscopy, because you probably have already heard about mass spec and probably have interpreted mass spec at this point, you're going to see a lot of lines on these printouts and the data reports that you're going to be given and be expected to figure out what these little jaggedy little lines mean as far as the molecules go. So before we go into the interpretation, I need to give you a little bit of background about NMR. All right, so first, NMR. Let's start with that abbreviation. We already know that this means nuclear magnetic resonance. All right. So let's break down these terms and kind of get our head around this concept of NMR. What is it doing? What is it focused on? And the very first one that I'm going to pinpoint is nuclear. That does not mean we're going to blow somebody up. Nuclear in this case means nucleus. So we're going to be focused on the nucleus of the atom. All right, so let's go back to general chemistry and let's talk about some basics of the atom. So here's the atom, and in the atom we have a lot of electrons that dance around and that are very free, and they can come and go as they please, kind of. Of course, all of this is just kind of made up in a sense as well, but we have electrons in these outer orbits of the atom to make up this layers of onion that we are bringing into our chemistry kitchen. All right. In the center is a core, and that core is made up of two subatomic particles. And this is what we call the nucleus, right? That was part of general chemistry back in the day. And the nucleus is going to consist of protons and neutrons. And those are my abbreviations for a proton and a neutron. A P plus for proton and a N for neutron. Neutron, of course, has no charge at all. Electrons are negative, and protons are going to be positive. So nuclear magnetic resonance means that we're going to be focused on the nucleus of the atom in order to look and interpret this data about these individual molecules that come my way. All right. Now let's talk about magnetic. Magnetic in this sense is going to mean that we are going to have to apply a magnetic field on these molecules in order for them to work the way that we want them to work. So just like a magnet, and many times in general chemistry, we've often talked about a positive and maybe a negative end, and we are going to be playing around with charges. So the purpose of the magnetic field is to induce a charge, in a way, on these molecules and have them all behave the same way and put some order to the chaos that's getting ready to happen. So magnetic fields are very important, and this is why the word magnetic goes into NMR. All right, so finally we get to resonance. And resonance basically means, can we manipulate, or a way that we can manipulate, the nuclei with magnetic fields. This is what it's going to focus on. All right, so here's the long story. We are going to induce resonance onto these molecules, which means we're going to manipulate the nuclei of the molecules or the atoms inside the molecule. And we're going to do that using a magnetic field. And that magnetic field, of course, is going to be targeting the nucleus in order for us to do what we need to do with it. So nuclear magnetic resonance. We're playing around with magnets, people. That's what we're doing. So the implementation of a magnetic field will allow us to generate data in a laboratory that's all about Structure. That is what this is over. What's the structure of the organic molecule that comes into play? So, how are the carbons connected together? Are they a straight line? Is it a branched carbon that will have maybe one carbon or two carbons off these branches? And these NMR spectra can be as complicated as the molecule's complicated, quite honestly. But for us, we're going to be focused on very simple molecules with very simple NMR spectra, so that way we can go through, dissect the spectra, really talk about and feel good about what that data is basically trying to tell us. Now, this is another form of spectroscopy, all right? And a lot of people get confused here because spectroscopy is the world of UV, it's the world of infrared, it's the world of mass spec, it's the world of AA, AE, and ICP. All right, well, what that means is that a UV uses a light bulb in order to do a job. The infrared uses something like light energy or a bulb to do a specific job, and you know what that job is. We've talked about it in this course. It's functional group identification. And then the mass spectrometer doesn't really necessarily use a bulb, but it uses somewhat like electron energy in order to do the fragmentation patterns of molecules as they come off from the machine. The AA instrument uses light bulbs and light energy to measure things like metals, so atomic absorption, AA, atomic emission, AE, inductively coupled plasma, ICP. All of those very similar. We are putting a bulb in a way into a stream of compounds, and that compound will absorb the light energy and tell us how much metal is present. And here in NMR, very similar. However, NMR doesn't quite use a bulb, right? Not all of these have to use a bulb, but we are talking about electron energy, and this means that we are talking about the electromagnetic spectrum. And when we talked about electromagnetic spectrum in a general chemistry course, we have often talked about the entire gambit. So we have a visible region that your little bitty eyeballs can see. Red, orange, yellow, green, blue, indigo, violet. And then there's a UV portion, and then there's an infrared portion, and that's where those kind of electron energies come from in a way. But there's also more to the story than that. And if you go back to a general chemistry course, you will remember what some of these others are. And the nuclear magnetic resonance technology will utilize an area of the electromagnetic spectrum in order to do its job. I'm not going to tell you what that is yet. That is to come in other lecture videos. But right now, just keep in mind that we are playing off of this radiation in a way in order for these molecules to do what we want them to do. All right? So the most important NMR that we're going to be talking about in this lecture series is HNMR. And HNMR basically stands for a proton. Okay, we are looking at hydrogens, and that's of course why H is out there in front. So HNMR is proton nuclear magnetic resonance. We also have other versions of NMR that's out there. One version of NMR is a carbon-based NMR. Another one could be nitrogen-based NMR. Another one could be fluorine-based NMR. Another one could be phosphorus-based NMR. There's tons of different ones that are out there. They're all kind of finely tuned to see what they want to see. And in HNMR, you are looking at hydrogens. What are hydrogens doing on the compound? CNMR will also mention in this lecture series, and CNMR, of course, represents carbon. So we are looking at what carbon is doing in the NMR. And then, of course, there's all of these other variations out there as well that people like to dance with and tangle with. But quite honestly, hydrogen and carbon are two of the most important parts of organic chemistry for sure. The reason for this, go back and think about structures after all this time. In organic chemistry, what have you seen, folks? You have seen compounds that are all carbon-based. And those carbon-based molecules have hydrogens on them almost everywhere across the board. So this is one of the reasons that hydrogen NMR is so important, because if I take something very simple, let's say ethanol, CH3, CH2, OH. Let's go to the ABC store and buy some Everclear because that's what ethanol is. So CH3, CH2OH, HNMR is going to be doing a test on ethanol, and HNMR will focus on hydrogens. And look at this. There's hydrogens here that it can report. There's hydrogens there that it can report. There's possibly a hydrogen here that it could report as well, depending on what we do with it. So we get this sense that we can get a little bit of everything about the molecule if we stick to our guns and do hydrogen NMR for our studies and for our reports. Well, someone along the course of the way said, now wait a minute, there's hydrogens here and hydrogens there and hydrogens there. There's hydrogens all over the place. So why don't we simplify this down a little bit, and why don't we focus on just carbons? Because if we focus on carbons, you're going to get an idea of the molecule. Maybe not exactly everything, but you're going to get a good enough idea of the molecule on how it's structured. So if you take a look at the structure, that carbon NMR would look at that carbon and would look at that carbon, and this would be okay and would be able to kind of figure out that part of the molecule. But here, it's going to actually ignore. It's going to be very difficult for carbon NMR to report anything about an OH group because there's no carbon that's involved. If I do nitrogen NMR on that molecule, I'm not really probably going to see anything at all. And the reason is because there's no nitrogens that are present in that molecule. So this is one of the reasons that HNMR is always talked about first, because all the molecules will have hydrogen in one form or another. And then the next one in line would be carbon NMR, that some people like a little bit better because it is a little simpler to read and to understand, but you're not getting a full picture of what those molecules are doing at that point. All right. So now what I want to do is give you very basics. I'm going to treat you like, this is the first time that you're seeing NMR, and I want you to pretend like you're in a kindergarten class. And that's the way that I'm going to explain this. So I want you to go into this knowing that this is not really scientifically how it is, but it is the basics. And that's really what we need from the course. It's the basics of how NMR is going to work and to do its job. And in order to do that, I need to oversimplify things. So that way it's probably a little easier to understand. So let's start with the M. We already said that M is magnets, all right? And we're going to be using magnetic fields. So when we look at nuclei, those nuclei that are out there and those compounds are all the same. It's all protons and neutrons. Make a general chemistry teacher happy. Well, if they're protons, basically we can think of these as little bitty magnets because those protons carry with them a positive charge, right? So many atomic nuclei, nucleus of atoms, atomic nuclei makes us sound fancy and smart. That's why we use it. But it just basically means the nucleus of atoms. You can think of those as little bitty small bar magnets, if that's the way that you want to think of them, with a north pole and a south pole. Oh, North Pole. Have you been a very good boy and girl this year? If not, Santa's not going to bring you anything. So North Pole and South Pole. And what we don't typically understand, because general chemistry doesn't do a very good job explaining it, is that, or really even introducing it at some point, is that these nuclei, they're not just stationary things. It's not just there. There's actually a spin that's associated with them. All right, so in order to put this in perspective, think about the planet that you are living on. I hope that's Earth, but it could be in your own little make-believe planet for all I know. I don't know. If it works for you, it works for me. So these planets will spin. They have a rotation to them. This is how we get night and day. And atomic nuclei are really not any different. Atomic nuclei, think of them as kind of ballish in figure, and they have a spin that's associated with them, or maybe a rotation. And the reason that we start with H NMR is because H is hydrogen. And let's think about hydrogen for a minute. Hydrogen from the periodic table has one proton, has one electron, and has 0 neutrons. That was something that we learned how to calculate in general chemistry. Look at your atomic numbers of the table. Hydrogen is atomic number 1. And that 1 up at the top means 1 proton, 1 electron, and it has a mass unit of 1. So mass of 1 minus the atomic number 1 is a 0. So this pretty much is a very simplistic way to look at what these atoms are going to do. And because it's just really a proton at this point, and that's it, then that makes the NMR, as far as description goes, a little bit easier for us. Plus, hydrogen's everywhere in the molecule, like we've talked about before. So there's tons of carbon to hydrogen bonds, tons of them. And this NMR will be able to pick out what these atoms are doing because they are focused on the nucleus, and that nucleus has a constant rotation with a North Pole where Santa lives in Atomland and a South Pole. So this is kind of the basics of any science course. There's nothing maybe surprising here, except the idea that these things rotate, and maybe you've just never thought about that before. Well, here's the problem. Let's say that I have a container, and that container has that compound in it. That container is going to have hundreds of thousands or millions of molecules that are all in that container. Maybe it's in a beaker, maybe it's in a flask, maybe it's in a sample container. I don't know where it's at, but there's tons of these molecules that are in there. And each one of these molecules, if I enlarge what that molecule looks like, could be a carbon chain with some carbons that are hanging off of it at this point. I don't know, I'm just making it up. We'll figure that out as we get to look at some of these examples. And now you need to go into this realizing that each one of these carbons have hydrogens on them. There's a hydrogen here, and a hydrogen there, and a hydrogen here. There's one here, there's one there, and there's one there. There's one here. There's 2 here to make 4 bonds. There's one there. There's one here, one there. There's 3 on this carbon to make it a total of 4. There's 2. And here's 3. Folks, that's a lot of hydrogens here, right? So the reason that I'm bringing up the spin of the nuclei and the rotation of the nuclei and the concept that nuclei have a north and a south is for this reason. You have a molecule. That molecule has multiple hydrogens. That means that each one of these hydrogens have a nucleus. That means that every single one of these nuclei will have a rotation because every single nuclei has a north pole and a south pole. That also means that these nuclei will spin, and they will spin maybe left to right. Some of them maybe could spin backward, right to left. Some of these could spin up and down. In other words, they can spin in whatever order they want to spin into. They can point in many different directions. We have no control of that, folks. That's just the way the molecule comes to us. So all of these hydrogens have nuclei. All the nuclei are spinning. All of the nuclei are spinning the way that they want to spin, and they're not necessarily all lined up perfectly in a row. And if they're not lined up perfectly in a row, it's going to be very hard for us to do any kind of studies with them. And the reason is because they're all over the place. How are you going to keep up with them? You can't. Too many variables that are happening here. So, one of the first things that we do in NMR is put the M in NMR. We put a magnet onto this molecule. And by putting a magnet that has a very strong magnetic field, attention! That's what happens to all of the protons. Oh, I see. We can put order to the chaos. The magnet will make all of these protons line up all in a row. All of their spins are going to be pointed in the same direction. So that is the purpose of the magnet. Spins in the same direction. Without the magnet, we would not be able to do this on that molecule. They're very comfortable in that position, right? They're perfectly okay. They don't really have to do anything. They can continue to spin. We're not taking that from them. And as long as they continue to spin, they get to do whatever they want to do without any gripes, moans, or complaints. So a magnetic field is placed onto the molecule, and that magnetic field, attention, makes all of them line up in the same direction, and they're still spinning, but it takes a variable away. I need you to think of this as like a little lazy kid that's on a swing. They're not going anywhere. They're very happy. They don't have to use their legs to push the swing. And as long as they don't have to do any work, those lazy kids are going to be perfectly okay on that swing, right? They just have to sit there, for goodness sakes. Well, today they probably will sit there on their phones. That's what they'll be doing. Their fingers will be at work. Their feet won't. So if they can sit on a swing and not really have to put any work involved and just sit there, they're lazy. That's what they want to do. And that's what these nuclei are doing as well. They're just sitting there. We've put them all onto a swing. We've put them all facing in the same direction on the playground, but they're not really doing anything. They can just sit there and wait. And those are perfectly fine for those nuclei to do that. All right, so here's an image that you might see in a textbook, depending on what textbook that you're using, if you're even using one. And here to the left, you're going to be seeing, here's just a kind of a representation of the nuclei just spinning in whatever direction they want to spin in. Doesn't really matter. So we put a little bit of energy into the system, and we put a magnetic field onto the system, and then we get this magnetic field to, attention, make them all line up. That is the very first step of nuclear magnetic resonance. The second step of nuclear magnetic resonance is, what do we do now? Right? So step number one, apply a magnetic field. And now we know why. All the nuclei have to line up in the same direction in order for us to do our job. And there's tons of them. And the easiest way to get them all to line up in the same direction is to apply a magnetic field on them. Step number two now is those little lazy kids that's on that swing, we're going to have to get them moving. We're going to have to get them to do something for us. And that's step two. So in the next video, we will look at step number two, and we will talk about what we have to do in order to get these little lazy kids to start swinging on the swing set. In other words, what do we have to do to the nuclei in order for them to give us a signal? Because that's what we're after. All right, so in the next video, that's where we'll pick up step number two. How do we move them? Come back. I'll be waiting.